This is lecture 3 on chapter 8, Atoms and the Periodic Table. So before we can get into more details about the periodic table, we need to talk about this idea. So this is talking about the atomic spectrum. And there are instruments out there that are called spectroscopes. You can actually build one. There are little templates that you can build. I'll actually post a set of directions online on how you can do this. You just need like a broken CD basically to create a reflective surface so that you can create one of these. The homemade ones are basically slit scopes, so you're looking through just a small slit to be able to break up the patterns of light that are coming in so that you can see them. Now, in a spectroscope, if you just look at white light, just white light, which is what we're seeing here, what you would see in a spectroscope is it's going to spread the light out. And since we're looking at white light, we're going to see all the different frequencies of the spectrum. So this would be like if you were looking at, say, sunlight coming in or light off of a fluorescent bulb or something like that. So you'd see all the different frequencies, red through violet, on both sides of this spectroscope. So why are we talking about this as far as atoms go? Well, the thing is that when we look at different atoms basically being burnt through one of these spectroscopes, what we see is that they actually have different frequencies. These different pattern frequencies. So for example, up here at the top is strontium, and here in probably beginning of next week, I'll get the videos started up showing you these flame tests here at home. Unfortunately, I can't send you guys kits or anything for you to do flame tests at home. We would have been doing them in lab. So you can see how this works. So when we take samples of, say, strontium, potassium, barium, copper, and we burn them, what we get is, if we show them in front of one of these spectroscopes, we get these kinds of readings. And instead of a complete, continuous, smooth set of light frequencies, what we get are specific bands. You can see there's just a few red, orange, no yellow really, some green, and a little bit of maybe green yellow, light blue, dark blue, and one way over here in the violet for strontium, and that's it. And you can see a very different pattern for potassium, lots of various bands for barium, and copper has very few bands. We've got some yellow, green, and a couple blue and a couple violet. The thing is that these atomic spectra are unique. They are fingerprints for every element. And so to figure out why, some scientists started to look at what was going on here. And by the way, what's really interesting about these atomic spectra, we actually use them now to help us identify what stars and planets that are farther out in the galaxy are made out of. So if you've heard of them talking about, a planet or a star containing certain elements, this is how we do it. We're actually reading the different atomic spectra or the different lights frequencies that are coming off of those objects. So Bohr is a scientist. I know, right? Again, another model or equation named after a scientist. So his model actually explains why these atomic spectra are actually forming. Why are we getting these bands for each element? So first, we're dealing with electrons. That's what it comes down to. So the potential energy of any electron depends on its distance from the nucleus. So the higher or the farther away it is from the nucleus, the higher energy it's going to have. And if you think about it, that makes sense from what we've talked about in previous chapters in physics, right? Think about like potential energy. The higher an object is, gravitational potential energy, the higher its gravitational potential will be. And this is the same idea. The farther away from the center of the nucleus the electron is, the more energy it's going to have. In this case, it's more like the stretching of a rubber band because we've got those opposite charges. And so those opposite charges want to be pulled back together. And so the farther you pull them apart, the more energy they're going to store. So how does it get that higher energy to get pulled from the nucleus? Well, when an atom absorbs photons, light energy, that atom is going to gain that energy. It doesn't just shoot straight through. It's going to absorb the energy from the photon, from that packet of light energy. And so the low energy electrons, the ones closer to the nucleus, are going to get boosted up. They're going to get boosted to what we call higher potentials. Basically, they're going to get pulled away from the nucleus. So they'll get pulled out, and then when they get kind of tired, if you want to think of it that way, they're going to give off their energy when they drop back down to those lower levels. So they are going to absorb the energy, jump out away from the nucleus because they're more energized, and then when they give off the energy, they're going to drop back down to a lower level, and that energy will go out. So what does that look like? Well, this is what we've got. So here we've got our atom with our nucleus and our electron that was just chilling down here in the low potential energy, so it's being very lazy and relaxed. The photon comes in, hits it, gets it very energized and excited. So it jumps up to that higher energy level. It gets stretched farther away from the nucleus. Like I said, eventually it's going to give up that energy. It can't stay at that high level. Think about like us. We can't stay at those high energy levels for a long period of time. Same for electrons. So eventually these high energy electrons are going to drop back down to their low energy, their lazy kind of states. And when they do that, the energy that they have left is going to be emitted back out, and it's going to be emitted back out as a photon. Will it be the same frequency as the photon that went in? No. It will actually have changed frequencies because some of the energy will have been absorbed by this boosting and dropping of the electron. And so this is a big part of how we're getting these atomic spectra, how we're getting these different frequencies showing up when we do something like ignite, lithium or something like that in a flame. So from this idea, we get the actual Bohr model. So the idea of the model is that you've got these electrons. When they get hit by photons, they jump levels. When they lose that energy, they drop back down. And so what the Bohr model shows is that electrons, I'm trying to get myself out of the way, there we go, have what we call discrete levels of energy. What we mean by that is, basically, it's the same idea of like us with steps. When you're going up the steps, you can only go from one step to the next. You can't go a half step. And so that's the same idea with electrons. They have specific levels that they can travel to. They can't travel in between them and stay there. So they have to go step to step to step, or kind of ring to ring to ring as they go up in those energy levels. So there's this principal quantum number, basically what we call n. N is just basically the level from the nucleus. So n equals 1 is the one closest to the nucleus, n equals 2 is the next one out, and so on and so on. So the number gets bigger as you go farther out. But the problem with the Bohr model is it doesn't completely explain the behavior of the electrons. It doesn't completely explain why we get multiple frequencies coming off of it when we get those electrons excited. So the model has been expanded. We still use the Bohr model because the Bohr model, one, is really easy to draw. But we still use a version of the Bohr model. But what we have found is that we have to add this in, and this was really weird when people started thinking about it, but it actually explains, sorry, my throat's getting dry, it explains why the electrons have those rings, why they only have the N1, N2, N3, instead of any in-between steps. So there are what we call electron waves, and these explain why electrons are restricted to particular energy levels. So I've got a picture here of what's going on. So here is this mechanism where it's not turned on. So that way you can kind of see what's going on. It's just a wire loop. And when they have it turned on, and they get it to the right vibration, when they get it to the right frequency, what they get is they get it to build up in what we talked about before as a standing wave. Now, when we saw these before, we were looking at them as, let's see if I can get my little pen up here. We were looking at them when they were attached at two ends, right, if you remember this, and they were going back and forth. So hopefully this looks familiar when we talked about sound. So we talked about them, that's not bad, kind of like this as a standing wave, where when the waves started to constructively and destructively interfere with each other, you got a buildup with the constructively interfered sections right here with the loudest sections. Well, that turns out to be what's going on with these electrons. So when they hit the right frequency going around the atom, they complete one full wavelength. So what I'm going to do is I'm actually going to stop here, and I have a video, that's what this link is up here, on the electron waves. I want you to watch that, and then I'll come back and pick back up with this. So I'll be back.